That is something I can agree with there. Yeah. All right, so guys, here we are, permutations. Again, yesterday with the introduction of combinations, not that we introduced it to you, for the first time. Again, obviously you worked through those before, but again, here in chapter 9, introducing combinations, we probably should have known that permutations weren't going to be too far behind, right? Again, it's almost like a package deal. It's just that yesterday we were actually using combinations in terms of, like being part of that binomial theorem. If we have combinations with word problems, again, where we're going here eventually, understanding the difference between combinations and permutations, it's very significant, but also relatively slight. Okay. By definition, we say that permutation of n different elements is an ordering of the elements such that one element is first, one is second, one is third, and so on. So whether we're talking combinations or permutations, basically we have the population, and we're going to create a smaller group. Okay, so we have everything, and we're going to create a subgroup. It's basically what's happening. If you have a big population and you break that down into a subgroup and the order matters, it's a permutation. If you have the big population and you break that down into a subgroup and the order doesn't matter, then it's a combination. Okay, so again, for the solver, it's really just a matter of which button you press on the calculator. But on the back side, like what that calculation is actually representing, it's pretty significant. Okay, so again, the go-to, the typical, and I think that we addressed these and talked about them yesterday. What if we said, all right, everybody, today for sure, grab your coats. We're heading down to the track. We're gonna run the mile today. We want to figure out how many we want to run. We want to finish. We're gonna place first place, second place, third place. First place wins $10,000. Second place, we're gonna give you $5,000. Third place, we're gonna give you $2,000. Does the order matter? I would say that the order matters greatly. The order matters quite a bit. That would be a permutation problem. So if there are 25 people in this class, 24 people in this class there normally are, if there are 24 people in the class, in theory, how many people could win first place? Only one person will, but how many, before that race starts, how many options do we have of winning first place? 24 options, okay? So we're just going to say that Becca wins first place, right? Becca's a cross-country runner. Okay, so I had about 18 different options of cross-country runners in here, but all right, she's pointing at Kara, so okay. She's fast. All right. We already said Becca, though. So again, Becca wins first place. Can Becca win second place? Or third or anything else? No, she already crossed the line. So if we had 24 options of first place, how many options do you really have for second place? Just 23. All right, so Kara got second place. Okay, Becca tripped her coming down the stretch or whatever, right? So Becca got second place, Kara got second place. Could Becca or Kara finish third? No, they've already finished, right? So how many options do you really have for third place then? Okay, 24, 23, then 22. That's how we would figure this out logically, but we have to agree that the order matters, right? Well, if I'm paying out, we have to do a lot of fundraising first, I suppose. That's the thing. Yeah. All right, so, but guys, hold on. So the example that we used yesterday, same example that we used yesterday, in case you forgot, what if we have 24 people in class and I've got 3 tickets to the Super Bowl that I'm going to give away? Does the order in which I hand out the tickets matter? Yeah, I was going to say, I think yesterday we talked about, all right, Caroline, Katie, and Allie, you guys won the tickets. Again, we drew your names out or whatever. Again, it doesn't matter the order in which I hand out the tickets. If I hand it to Caroline, then to Katie, then to Allie, it's not like again, exactly as I said yesterday, it's not like Allie's going to complain, well, you gave me the third ticket. No, you're still going. And whatever order I pass out the tickets, it's still those 3 people are going to be going, and the other 21 of you, sorry, you got nothing, right? But that's the difference. That would be a combination problem. We had 24, and we're choosing 3. All right? So permutations, once again, we're going to have 2 different types of permutation. We're going to have a full permutation, and then we're going to have where we again, it sounds weird, but we have n objects selecting r at a time. Okay? So again, the full permutation is going to look something like this, where we want to find the number of permutations of n elements it's just going to be found with n factorial. That's if we're doing the entire thing. So again, imagine that we're talking about going down and running the race. As we started, 24 options for first, 23 options for second, 22 options for third. But what if we kept going? How many people, or how many ways could you finish fourth, fifth, sixth, all the way down to 23rd, 24th place, right? Wouldn't that just keep on going in pattern? 24 times 23 times 22 times 21 times all the way down. It's going to really just be 24 factorial, isn't it? But the next one, the permutations of n elements taken r at a time, that's when we say like, we don't need the entire permutation. How many ways could we finish first, second, and third? That's creating the subgroup. Does that make sense? All right, so typical example, again, just trying to be very generic. What if you have the letters A, B, C, D, E, and F? How many different possible ways could we rearrange those? So, what was it? 720. Good, I agree with you. How'd you get there so quick? Yeah, so if we're trying to fill 6 spaces, don't you agree that we have 6 options for that first spot? So let's just hypothetically say that we use C. Can't use it again, so we really only have 5 options for the next. Okay, it looks like we used E. Well, we only have 4 options here, and then 3, and 2, and 1. Easier written as 6 factorial, or as you're saying back there, 720. I agree. That's, again, what we would refer to as a full permutation. Okay? The more common type is when you have n elements taken r at a time. Again, a little bit more like this. Again, going back to the whole idea of running a race. This time we're talking about horses, though. 8 horses running in a race, and how many different ways can these horses come in first, second, and third? So 2 ways of looking at this logically. First, second, third place. We have 8 horses. That means we have 8 options of who could win first place, right? If Seabiscuit wins first place, can't win second place or third place, right? So how many options for second place? 7. All right, Secretariat got second place, can't win third. How many options for third? Yep, 6, and I'm fresh out of horse things. But this is how we're going to find it out. 8 times 7 times 6. What is 8 times 7 times 6? 336. Good. All right, that's, again, thinking through this logically. Just, okay, we have 8 horses. We're trying to finish first, second, and third. In theory, yeah, we could go about this. We could also create the notation, okay? NPR. N is always going to be the larger number, so 8P3. Now, please don't write this down, but I also want you to see it. First off, is there a button on your calculator that you could type this in? I'll put it this way. If you could find the combination button yesterday, the permutation button is going to be right there next to it. Okay? But yes, you can absolutely type this in on your calculator. So, we have a formula for this, and the formula looks something like this. If we were to say that n is 8, we've got to go n factorial, so 8, 7, 6, 5, 4, 3, 2 times 1 in the numerator, over n minus r factorial. So n is 8, r is 3, 8 minus 3 is 5, factorial 5, 4, 3, 2, 1, and we're going to cancel a whole bunch of stuff out. Now again, this works, it's true, but man, there's a shortcut. I'm saying not quite the shortcut of use your calculator, but here's how, if you're ever doing this by hand, I would encourage you to think through it. The first number, n, the one on the left, bigger number, you're going to do that factorial. So 8, 7, 6, 5, 4, 3, 2, 1. But you're going to stop after r terms. First, second, third term, that's where we're going. That makes sense how we got there? Now again, that's 2 very different ways of looking at 8 times 7 times 6 in terms of how we got there logically compared to how we got there with permutation notation. But the answer is going to be the same. Okay? Or, once again, type it in on the calculator. All right, so guys, this next one, to me, this is crazy. Again, just the math nerd in me, I suppose. That again, it's hard to even fathom. But does everybody know what I'm talking about when I'm talking about a pool table, billiards, all that stuff? All right, so again, a lot of different games you could play, but again, we're saying that, again, you got a pool table, and there are 16 balls on the table. Okay, you have the cue ball, the white ball, and then you have 15 numbered balls, 1 through 15. Okay, so just imagine if you know somebody with a pool table, or maybe you have one in your basement or something like that. Again, imagine that you're going to play a game, and you take all the balls out of the box, you just roll them down to the end of the table, and you got all the balls that are just lined up at the end of the table. how many different ways could those balls be ordered? How many different ways could they line up? All right, a lot, right? So I'm sure that all of us are going into this problem thinking, yeah, there's a lot of different ways you could do that. Okay, do we agree that you have 16 options for the first, then 15 options, 14, all the way down to 1? More commonly written as 16 factorial, right? Okay. But what is 16 factorial? It's 20 what? Trillion. I gotta keep up here. 922,789,888,000 different ways. Is that just making anybody else's head explode? Okay, that is insane. Because, again, most of us have probably played pool before. Most of us have probably, done this exact thing to where, again, I mean, the number would be slightly different because then we'd be using 15 balls instead of 16. But imagine that you put absolutely no thought into it whatsoever, and you just put all the balls and you rack them up in the triangle. How many different ways could you do that? Close to 21 trillion ways. That's insane to me. So again, all right, I've got a pool table at home. And I had a pool table when I was, my dad, he was big time in the pool and stuff like that. So again, there was a pool table in my house ever since before I was born. So I played a lot of pool over the years. I couldn't even guess how many games. But if there are close to 21 trillion different ways that you could wrap them up, that means that of all the games that I've played over the years, how many different ways have I probably racked the balls? I maybe have hit like 0.5% of the ways that are possible, something like that. It's insane to me to start to even fathom how big of a scale we're talking about here. Yes. When you rack them up? I was going to say, usually you got to put the 1 ball first and the 8 ball goes in the middle. But other than that, there are certain games that you're supposed to go like solid stripe, solid stripe, solid stripe, solid stripe, solid stripe, solid stripe, like that. 8 in the middle. But again, there are other games where it doesn't matter at all. All right? All right, so again, 21 trillion, that's just too big to really comprehend, quite frankly. So what if we were saying, all right, you have 16 balls on the table, but you're just going to grab 3 of them and put those in order. How many ways could you do that? That means now we just have 3 spots to fill. We have 16 options, 15 options, 14 options, right? Or we could say 16 P3. What's that going to be? 33. All right. Okay. Last thing we're going to have a chance to talk about today here, distinguishable permutations. Okay, this is going to be made a lot simpler if we actually understand what the word distinguishable means. Okay, so distinguishable, what we're getting at means that like you look at it and you can tell a difference. You could distinguish a difference between the two. So like for instance, can you distinguish the difference between these 2 blue pens? Yeah? I would look close to them. They are identical to each other. But now can we distinguish? No. Took the cap off of one, right? We could tell a difference between the 2. Right? So, guys, stay with me. Stay with me. Okay? If we're talking about distinguishable permutations in this class, there are other options out there, but in this class, anything dealing with distinguishable permutations, it's always going to start the exact same to where you're given a word. All right, so our job, our task is how many distinguishable ways can the letters of the word banana be written? Okay? All right, here we go. I'm going to jumble these words up, or these letters up. You ready? All right, jumble them up. Can you distinguish the difference between what I just did? No. Okay. Well, of course, just being facetious, I'm going to say, no, I switched those 2 A's around. Well, we can't distinguish the difference. So what we have to do, again, think back to the first example where we had the letters A through F. We said that there were 6 factorial different ways of doing that, right? 720, there were 6 factorial ways because there were 6 letters. We have 6 letters again here. But I have to divide out all of the repetition. So where's the repetition going to come from? 2 A's. Well, how many? We have 3 A's. We have 3 A's. I'm going to have to divide out the 3 factorial. How many N's do we have? We have 2 N's, so I'm going to have to divide out 2 factorial. I mean, if we want to make it weird, how many B's do you have? 1. So, I mean, if you really want to think 1 factorial, but that's going to do nothing for us. So please, I need everyone's attention. I know the bell's going to ring here in a second, but are we all on the same page that 6 factorial, I can't just say 3 factorial, 2 factorial, that's all going to cancel out and be 1? We understand that's not going to work that way, correct? All right. So what do we get when we cancel these all out?